Hey Ramblers! This video covers chapter 8.2 in our textbook, and it introduces us to the concept of similarity. Now, similarity is as central to the second semester as congruence was to the first semester, and it's really applicable to courses and to situations outside of the geometry classroom. Similarity will be a big part of any kind of an art class where you're doing any drawing or trying to get a sense of perspective and making some objects in a drawing look farther away than other objects. If you do any kind of design, whether it be design of in architecture or in a car where you're doing 3D design, models and ratio and proportions and similarity are really central to that. We put models up of cities. We put models up of buildings. You really want to understand similarity and not turn out like our friend Derek here.
Let's get back to the reason that we're really here. Without much further ado, I give you the Derek Zoolander Center for Kids Who Can't Read Good.
What is this?
A center for ants? What?
How can we be expected to teach children to learn how to read if they can't even fit inside the building?
Derek, it's just a
I don't want to hear your excuses! The center has to be at least 3 times bigger than this.
Let's start by defining similar figures. Similar figures have the same shape, but are different sizes. That's due to the fact that they have the same size angles, but the sides are different sizes. In fact, the sides, as we'll see, are all proportional. There's 2 important terms. A dilation is larger than the original, and a reduction is smaller than the original. Let me make a reduction of this pentagon that I've made. As you can see, this figure A prime, B prime, C prime, D, E prime is a pentagon which is 1/2 the size of the original pentagon. So it's a reduction, and it's a similar figure to the larger pentagon. In fact, if we were to take a look at the definition of similar polygons, we see that similar polygons are polygons in which the corresponding angles are congruent. And just looking at 2 different pairs, we can see that angle BAE in the larger pentagon is equal to BAE, B prime, A prime, E prime in the smaller pentagon. Same means angle BCD in the larger pentagon is congruent to angle B prime, C prime, D in the smaller pentagon. So similar polygons have corresponding angles that are congruent. But the lengths of their sides are not congruent. They're proportional. So if I compare any 2 corresponding sides, like ED to the entire, E prime D to the entire side ED, and put them in ratio, I see that it's a 1:2 or 0.5 ratio. If I compare another side, let's say A prime B prime compared to AB, and divide, I will also get 0.5. So similar polygons have congruent angles and proportional sides. Let's quickly look at a theorem which is a consequence of the proportionality of the sides. Let's take a look at the hexagon here, A, B, C, D, E, F. And I can measure each one of these sides. And if I add them all together, I get the perimeter calculation. Now let's take a dilation of this hexagon, a smaller version, and I'll construct that. All right, let's measure the sides of this dilated hexagon and also look at its perimeter. Now, if I compare the perimeter of the small hexagon to the perimeter of the large hexagon, it should be the same ratio as the ratio of the sides. And I set the small hexagon to be 1/3 the size of the large one. So let's take a look, see if it works. And sure enough, when I compare them, I do get the ratio of the sides. Sure enough, when I compare the ratio of the perimeters of the small hexagon to the large hexagon, it's the same as the ratio of the sides. Let's get that theorem down. So the last theorem for this video is that if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their sides. Okay, thanks for watching, Ramblers. I hope this video helps.